So the next talk is about secure multi-party computation with sublinear processing. It is going to be given by Ariel and based on a combined work with Verifier, and duality.
Thank you for the introduction. So I'm Ariel, and I will present the paper Secure Multiparty Computation with Sublinear Processing.
Sorry.
Okay, everyone is okay? Okay, so in this talk, we consider the standard setting of MPC. We have n parties who wish to compute jointly some functionality which is represented by an arithmetic circuit with addition and multiplication gates, a circuit that may be defined over a field or a ring, with malicious security and dishonest majority. Now we know that a very popular approach in the dishonest majority setting is to work in the preprocessing model. So in this model, the computation is divided into two phases: an online phase and an offline phase and an online phase. And in the offline or the preprocessing phase, the parties generate correlated randomness, and in the online execution, they consume this correlated randomness to compute the desired functionality. Another way to look at this model is to view this execution as an execution with a trusted dealer that gives the parties correlated randomness, and then later design a protocol to securely distribute the dealer. And the advantage of using working in this model is that we can move all the expensive public key crypto machinery which is unavoidable in this setting to the preprocessing and obtain an online execution which is fast, cheap, and basically information theoretic. So the three main metrics that we will look at, that are typically considered in this setting, is the communication cost of the online and offline separately, and the size of the correlated randomness that needs to be stored by the parties. So, how do we usually work in this model? So we usually use Beaver triples, right? So here the dealer gives the parties shares of random multiplication triples, and these are used to multiply shared values in the online execution with very low communication, as can be seen in this table. What's important is that the communication per multiplication gate per party is constant, and therefore the overall communication to compute a circuit grows linearly with the size of the circuit. So this is for semi-honest security. To achieve malicious security, so the leading approach in the last decade or so is the speed approach, where basically the dealer gives the parties authenticated Beaver triples. And the advantage of using this approach is that the online communication cost basically remains the same as the cost with semi-honest security. However, the correlated randomness clearly grows for large fields by a factor of 2, for small fields or rings by a factor that depends on the security parameter. And the offline cost is usually the bottleneck of this approach. And there's a long line of works. Many people here in the audience were part of the effort to reduce the cost of the offline, but still this is the main bottleneck of this approach. There are other approaches as well, which I will not discuss at all, but they give different trade-offs between the online and the offline. But I think only the speed approach as the property that the online cost is the same as if we use semi-honest security. Right. So how can we solve the bottleneck of the offline, of the expensive offline cost? So a new direction in MPC, which I'm sure will be mentioned in this workshop as well, is to achieve silent preprocessing using PCGs, pseudo-random correlation generators. And the idea here is that the dealer will give each party a short seed, a short correlated seed, and then each party can locally expand his seed to receive shares of authenticated triples. Right, that's the idea. And if we had such an amazing tool, then the online cost would remain the same, but then we would be able to compress the correlated randomness, because now each party needs only to store his short seed. And also the offline cost will become sublinear, because the parties will only need to interact to generate these correlated seeds. However, this tool still does not exist, or at least is only partially exist. So currently, we have only completely efficient PCGs for generating unauthenticated triples. So to achieve semi-anonymous security, we can definitely use such a tool. But for malicious security, we currently have only completely efficient PCGs for authenticated triples for only two-party computation over large fields. So what can we do meanwhile, or as an alternative? So in this work, we suggest we use a different approach that kind of achieve the same desired goals, the same efficiency goals. And the idea of our approach is that the parties will run a semi-honest computation first. For the semi-honest computation, the parties only need to use unauthenticated beaver triples. And then they run some additional lightweight short verification step, which consumes some extra amount of correlated randomness. However, this extra amount of correlated randomness is sublinear in the size of the circuit. This means that now the dealer basically needs to give the parties seeds for generating unauthenticated beaver triples, okay? Not authenticated, just simple unauthenticated beaver triples, and the extra correlated randomness for the verification, which, as I said, is sublinear. So now when we want to distribute the dealer, so basically we can use any sublinear protocol for generating unauthenticated triples. For example, use PCGs for unauthenticated triples, which we have already. And for the second part, for generating the extra sublinear amount of correlated randomness, because the size of this extra correlated randomness is sublinear, we can use standard MPC tools with sublinear communication costs. So overall, the amount of correlated randomness is sublinear, and also the cost of distributing the dealer is also sublinear. So what we get, right? So if we summarize our results, so what we get here is a protocol in the preprocessing model to compute any arithmetic circuit with sublinear offline communication, cost which is square root in the size of the circuit, sublinear amount of correlated randomness, information theoretic online phase. As before, the security of the protocol is based on any sublinear communication protocol for generating unauthenticated beaver triples. And for the second part, what we need is basically only additively homomorphic encryption. So this is the result. Yeah, so to compare ourselves to previous work, so we talked about the cost of the speeds approach. So in the second column, you can see a previous result with the same set of authors, the BGIN 21 paper from Crypto 21, where we already showed how to compress the correlated randomness to be logarithmic in the size of the circuit, but still the offline communication cost was linear. In this work, we increased the size of the correlated randomness, but it's still sublinear from logarithmic to being square root. But this allows us to achieve also offline with sublinear communication costs. Okay. So yeah. So the main building block that we use for our verification protocol is zero knowledge, fully linear proof systems due to Bonnet et al. From Crypto 19. So in this proof system, we have a prover who wants to prove some statement over an input X. And this system works by letting the prover output a proof, pi. And then there is some public randomness that is being chosen. And based on the public randomness, there are some queries. There is a vector of queries, Q, that is being set. And then the idea is that the verifier can only make linear queries to the input and the proof, which basically means that we can multiply the query vector with the vector of proof and input. And the verifier sees the answer, and based on the answer, it needs to decide whether to accept or reject. That's the idea of this proof system. As I said, the main property is that the verifier is allowed to run only linear queries to the input and the proof. This is why it is called fully linear proof system. You can define here variants which have only one such interaction or multiple rounds. In this work, we only need one round. And of course, we can define complete soundness and zero knowledge in the standard way. So this is somewhat an abstract idea, but from this abstract notion, we can derive a very practical tool, which is called distributed zero knowledge proofs. So here we will have, instead of one verifier, multiple verifiers. And then we can instantiate, or we can realize this idea of making only linear queries. So how do we do that? So now we will assume that the input is also distributed across the verifiers. Or in our setting, the input X will be secret shared across the verifiers. So now the prover, we will ask the prover, when he outputs a proof, to also secret share the proof in the same way. And now each verifier will locally query its shares of the proof and the input. Now, if the secret sharing that we use for sharing the input X and the proof pi is linear, this means that each verifier will obtain a secret sharing of the answers to the queries. And therefore, they can simply exchange their answers and obtain the answers, and based on that, decide whether to accept or not. And what Bonnet al showed in the paper is that if X is robustly shared across the parties, robustly shared meaning that the shares held by the honest parties are enough for reconstructing the secret. And if the statement to be proven is a degree 2 polynomial over the input X, then there exists a distributed zero knowledge proof protocol with sublinear communication and with soundness that holds even if there is a collusion between the prover and a set of the verifiers. And this tool with this result is very useful to achieve malicious security in MPC. Because in order to prove correctness, what we basically need is to prove that multiplication were carried out correctly. And this can be represented, this is a statement that can be represented using a degree 2 polynomial over inputs that are shared across the parties, because after the parties compute the circuit, the inputs and outputs of each multiplication gate is shared across the parties. And indeed, in the honest majority setting, this tool was used to achieve malicious security with sublinear additive overhead, relying on the fact that the secret sharing in the honest majority setting is inherently robust, right? Each secret, the honest parties themselves can reconstruct each secret. However, when we move to this honest majority setting, so the main question is how to achieve robustness without increasing the amount of correlated randomness. So in the previous paper, in BGN21, we presented the two main technical ideas to solve this challenge was to first define a robust secret sharing scheme using the dealer, which we call star secret sharing scheme. And second, to maintain this property that we have of the robustness that we have also throughout the verification protocol. And we do that by using the dealer as a verifier in the distributed zero knowledge proof. That's the two main technical ideas. So how does it work? So first of all, what is this star secret sharing scheme? So this scheme is basically used everywhere. So the idea is that we maintain the following invariant over the wires of the circuit. So for each secret that we want that the parties need to store, to share, that then each party will hold the mask secret, and the dealer, and also the mask secret, and also a share of the mask, and the dealer knows all the shares of the mask. Right, so this is used everywhere, and this gives us the robustness that we need because now each secret can be reconstructed by each party and the dealer. Right, so this is basically what we need. And as I said before, this basically is used in many semi-honest protocols. For example, if we will take the semi-honest protocol that uses Beaver triple, so we have this invariant, for example, in the circuit independent model. So we have this invariant on each input to each multiplication gate. Right, so we have this tool. So now the question is how we can maintain this type of robustness also in the verification protocol. So the idea is the following. So first of all, what do we want to verify? So basically, we want to verify that each output to each multiplication gate is consistent with the inputs. In other words, now we can write this equation. In other words, by replacing each secret by the secret plus by the masked secret plus the mask, right? This is exactly the same thing. And of course, the parties want to verify all multiplications in one shot. So basically, what they want to check is that this equation holds. Basically, that taking the random linear combination of all the equations for each multiplication gate results equals 0. So this is the equation. This is basically the equation that the parties want to verify. If we look into this equation, so we can see that all these values are basically known by the parties. These include the random coefficients, the alpha k's, which are chosen jointly by the parties at the beginning of the verification protocol and become public. So these are known by all parties. And we have the masked values, the z, x, and y hat, that are also known by all parties because these are the masked values that the parties have seen during the semi-honest computation. On the other hand, these values, these are the masks, are known by the dealer. So each value in this equation is either known by all parties or by the dealer. If we open this equation and do all the math, what we will get eventually is that this equation can be reduced to simply checking that the inner product between two vectors, a vector A, which is known by all parties, and a vector B, which is known by the dealer and also shared to the parties, equals to 0. So the entire verification boils to verifying that this equation holds. So now, so first of all, we can see that this is indeed a degree 2 polynomial, which is good for us, right? And also that the input is basically shared in a robust way with the same robustness that we defined before, meaning that each value is known by either an honest party or by the dealer. So we know that there exists a distributed zero-knowledge proof protocol with sublinear communication cost and with soundness that hold even if the prover colludes with a subset of the verifier. So now the only question is how to emulate this distributed zero-knowledge proof protocol in our setting. So how will it work? So we will use the dealer as one of the verifiers. So on the one hand, we have the parties who know all the values in the vector A. And on the other side, we have the dealer who knows all the values in the vector B. And what we would like for the prover to do is to take the proof and also share it to the parties and the dealer in the same way, meaning that the parties will see the masked proof and the dealer will know the mask. So once we have this, it means that each piece of information here, the input and the proof, are additively shared between each party and the dealer. But because this is also a linear secret sharing scheme, this means that each party and the dealer can make the linear queries independently. And then what we will obtain is also a star secret sharing of the answer, meaning that the answers are also secret shared by, additively shared by each party and the dealer. So this is what gives us the robustness of throughout this protocol, which eventually leads to soundness, meaning that malicious parties cannot cheat here. So the only question that remains is how to emulate the prover, right? Because who is the prover here, right? No one's known the statement, the statement is known. No one's known the input. So who is the prover here? So the answer is that the prover is also emulated by all the parties. And here we use the fact that we said before that the vector B is known by the dealer, but is also shared by the parties. Right? The vector B basically contains all the masks from the semi-honest computation, so each party holds an additive share of the mask. So this means, and we can show it, it's very simple to show that, therefore, that each party can compute an additive share of the proof. So now, once each party locally computes an additive share of the proof, so it can simply star share this its additive share to the other parties by broadcasting a masked version of its additive share, and then the parties can simply locally add all the masked additive shares. This means that now each party knows the masked proof, and since the dealer gives all the masks to this additive shares, he knows the dealer knows the masks. So this is basically what we need, and therefore it means that we can emulate the distributed zero-knowledge proof protocol and obtain what we need. So if I so to summarize what we did, so how the fact that we use the dealer helps us in this process. So as we saw, because each piece of information is known by an honest participant, meaning an honest party or the dealer, this is what gives us the robustness that we need, and this leads to the soundness of the proof, meaning that no one can cheat. And the fact that the statement to be proven is a degree to polynomial, it means that in this protocol we have sublinear communication. And because communication is sublinear in the input size, and because the verifier, what he does basically is he acts as the dealer, acts as a verifier in the protocol, it means that also the messages from the side of the dealer are their size is also sublinear in the size of the input. And therefore, the correlated randomness that eventually the dealer will give, because its messages will eventually be given as correlated randomness to the parties, is also sublinear in the size of the input. And because the dealer basically performs only computation over random data, it can basically pre-process its computation and give all the messages that it needs to send as a verifier. It can give it as correlated randomness to the parties. Right. So this is So this is the idea. Okay, so I see that I'm a little bit running out of time. So we have also some concrete costs that we show in the paper. Let me jump to how we can distribute some, but now let's jump and see how we can distribute the dealer's work with sublinear cost. So what the dealer actually does. So this, of course, depends on how we actually instantiate the distributed zero-knowledge proof protocol, which I didn't show, but with the instantiation we give in the paper, basically what the dealer does is the following. So basically the dealer needs to define a square root amount of polynomials. These are the G polynomials here. The degree of each polynomial is square root in the size of the circuit, and the dealers need to evaluate each of these polynomials on a random point tau. And the evaluation of these random polynomials is basically the correlated randomness that he gives to the parties. So, right, and we have square root polynomials, so the amount of correlated randomness is square root. Now, these polynomials, how are they defined? So they are defined based on the Bieber triples, which the dealer also needs to give to the parties. So this is what the dealer does. So now when we want to distribute the dealer's work, so what we can do is the following. So now we will want the parties to generate encrypted versions of the powers of the random point tau. And if we use an additively homomorphic encryption for these values, so now each party can take his shares of the Bieber triples, define the polynomials over his shares, and then use the homomorphic property of the encryption scheme to basically evaluate them locally and obtain an encryption of each share of the evaluation of each polynomial. And then the parties can simply exchange their ciphertext and perform secure decryption. So So if we look at this process, where do the parties need to interact? So first of all, the parties need to generate encryptions of the powers of tau. But because the size here is sublinear in the size of the circuit, so we can use any general MPC to generate this square root amount of ciphertext, and this will result with sublinear with square root cost. So for generating the Beaver triple, as we said before, we can use, for example, PCGs for unauthenticated Beaver triples. And finally, the parties need to interact in order to decrypt square root amount of ciphertext. So overall, the amount, the cost is sublinear in the size of the circuit. So this is how we distribute the dealer. Of course, there are some more details here. So what I showed is basically gives us directly offline with semi-honest security, offline with semi-honest security for online with malicious security. We can use generic tools to achieve offline with covert security, relying on the fact that in order to check an instantiation of what I showed before, you can simply commit to the PCG seeds, and then simply open the seeds and open the random point tau, and then you know if cheating took place or not. Finally, to achieve malicious security, so feasibility-wise, we can use any generic compiler, generic communication preserving compiler to achieve malicious security, but of course, this will not give us efficiency, continuous efficiency. So to achieve continuous efficiency, the main challenge here is that what happens if a malicious party does not use its correct Beaver triple share, right? It does not use the actual share that he received from the PCGs. So this is a problem, and for this we need to add some more tools on top of what I showed. For example, to use some success commitment and to prove that the parties used the values that they committed to. And this will also require us to use another assumption for the additive homomorphic encryption scheme, which is called linear only assumption, which is seems plausible. Yeah, anyway, so I see that I'm running out of time. So thank you very much.
Maybe just a couple of quick questions if anyone has. Okay. Maybe you can just.
Oh,
for the
I had
online.
a short question. Just,
Okay.
What's the size of the circuit is just the number of multiplication gates or all the gates?
Yeah, the size of the circuit is the number of multiplication gates. Yes. Yes.
And this paper is where?
Yeah, it's not online yet. I mean, it was published in Eurocrypt, so there is the preceding versions, but the full version is not published yet. Yeah, I apologize.
And the PCGs are these congruential generators? Or PCG?
Yes.
This is the permuted congruential generators?
It's pseudo-random correlation generators. Okay. It's like PRGs, but they generate some correlations. Yeah. For example, Beaver triples.
Okay, thanks.
On some much earlier slide, you talked about how to distribute the prover. And there you said something like each party computes a share of the proof. How's that possible? I mean, presumably the prover works in secret data, so that can't just fall out of the sky, I suppose.
No, because the proof is basically right. So we have this inner product between two vectors, right? One vector is known by the parties, and the second vector is shared to the parties. So the parties can locally compute an additive share of the inner product. So basically, the proof is basically some inner product of. So basically, this is what they do actually.
Maybe one last question. Okay.
Can you talk about the round complexity of all these constructions which try to optimize?
So the round complexity of the verification, for example.
In which you compared your work with previous works in terms of communication complexity.
Again, the round complexity of
online and offline round complexity.
Yes. So the online complexity basically remains the same as the online of the semi-honest computation, which is the depth of the circuit. For the offline, so I think it should be also some sublinear, because you only Yeah, I think it should be sublinear in the size of the circuit because you can do all the decryptions in parallel. And basically, you need only to generate the encryptions of the power of the random point tau. So basically, I don't think you need more than square root rounds for that.
Okay, I guess we're taking questions of time and let's find the speaker again.